4, we talked about the relationship between two variables. We're going to continue that discussion in Chapter 5, talking about regression. The main idea in simple linear regression is to exploit the relationship between two variables so that it is possible to gain information about one variable, the response variable, if information is known about the other variable, the explanatory variable. The process requires first discovering the relationship between the variables, and then, knowing this relationship, constructing a model, in this case a straight line model, that relates the response to the explanatory variable. As emphasized in the previous chapter, the distinction between explanatory and response variables is critical. The concepts we'll cover here. We'll talk about the least squares regression line, residuals, influential observations, and the notion that correlation does not imply causation. The main objectives will quantify the linear relationship between an explanatory variable and a response variable. We'll use a regression line to predict values for particular values of x, calculate and interpret residuals, and describe cautions about correlation and regression. So to begin with, a regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. We can use a regression line to predict the value of y for a given value of x. So, for example, in a study, 16 women subjects watched as a man's hand was zapped with an electric charge. The brain activity for the women was recorded, and the women also completed a survey on empathy. For an empathy score of 70, what is the predicted level of brain activity? Well, we can look at the scatter plot along with a regression line. The regression line describes the overall pattern of the relationship. And for the empathy score of 70 along the x-axis, the horizontal axis, we can just kind of climb up to the line and then work our way over to the y-axis, and that gives the predicted response for empathy score of 7. Okay, now suppose you want to find the best fitting line for the data shown. It might look something like this. Now suppose you're asked to find the best fitting line for the data shown below. It might look like this, or it might look like this, or this, or this. So what is the best fitting line? Well, suppose we draw a line among the data points in any direction. And now let's consider the distances from each data point to any particular line that we draw. What we want to do is find the line that has the smallest total error. So the smallest total distances between the points and a particular line. So one way to accomplish this is to insist that we find the sum of the squared distances that has the smallest possible value. Since we are trying to predict y, we want the regression line to be as close as possible to the data points in the vertical direction, in the y direction. The line that minimizes the sum of the squares of the vertical distances of the data points from the line is called the least squares regression line. Okay, so you probably remember from algebra we have the equation of a line, y equals mx plus b. The regression line in statistics is usually written slightly differently, but the components are pretty much the same. We call the predicted value y hat, and the intercept, the y-intercept is a, and the slope is b. So x is the value of the explanatory variable. Y hat is the predicted value of the response variable for a given value of x. B is the slope, the amount by which y changes for each unit increase in x. A is the intercept, the value of y when x equals. So, the equation of the regression line. This is just for information purposes because I'm not going to ask you to actually use these to calculate. You'll use software, computer software, to actually do the calculation of regression lines. But I wanted to point out the equation or the formula for finding the slope is the correlation coefficient R times the standard deviation of the y values over the standard deviation of the x values. Remember, standard deviation measures is a measure of how far things are apart. So basically we're saying the change in y over the change in x. And the value for A, that is the y-intercept, equals the mean of the y values minus B times the mean of the x values. Just kind of a curious arrangement of. Okay, so let's talk about prediction with using the regression line. For the empathy brain activity example, the least squares regression line is y hat equals 0.0076x minus 0.0578. Y is the predicted brain activity for any empathy score x. Suppose we know that an individual has an empathy score of 70. What would we predict the brain activity for that individual? Well, we predict the brain activity to be, we simply plug in the number 70 into that equation. So where x is, we plug in 70 for x. And solving, we get a brain activity of 0.4742. And if you remember the graph that I showed earlier, we see that the horizontal line, dotted line, with an empathy score of 70 hits right around 0.4 something. So that goes along with what we observed earlier. Here are some facts about least squares regression. The distinction between explanatory and response variables is essential. The slope B and the correlation R always have the same sign. The square of the correlation R squared is the fraction of the variation in the values of y that is explained by the least squares regression of y on x. R squared is called the coefficient of determination. I'll explain that a little more. So, for R squared, notice in the first scatter plot the data points fall exactly on the line. So the variation of y is completely explained by the regression equation y equals a plus bx. There's no variation from the line. And if we plug in an x value, we can completely predict where it's going to land, what the y value will be. For the second scatter plot, the data points don't fall exactly on the line. There's some variation of the y values around the line. For the most part, y is related to x by the regression equation. Y is close to equaling a plus bx, but not all the variation is explained by the regression line. For the third scatter plot shown, the data points are near the line, but there's a lot of variation of y values around the line. So y is somewhat related to x by the regression equation. Y is kind of equal to a plus bx, but there's a lot of variation that is not explained by the regression line. So that's what R squared is, the coefficient of determination. Residuals are an important analytic tool in regression. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. So y minus y hat. A residual plot is a scatter plot of the regression residuals against the explanatory variable. And we use it to assess the fit of a regression line by looking for random scatter of the residuals around the line 0. So, for example, suppose we have the percent outsourced maintenance versus percent flight delays for several airlines. And we see there's a nice line there and the points are scattered around. If we look at the residual plot, we see that the points are scattered around the line y equals 0, and there doesn't appear to be any real pattern to those. So effectively we say that the scatter, the variation of the data points around the regression line is basically random, and so a linear model is appropriate. Now suppose we have a scatter plot here that shows the speed of a car versus its braking distance. And we have a nice line, regression line. We can get an equation. The correlation in this case is very close to 1, 0.984. Very strong. And we can calculate the equation of the least squares regression line. So a linear model is good, right? Well, maybe not. If we look at the residual plot, there's a clear pattern to these residuals. This indicates that the variation around the regression line is not random, and therefore a linear model is not appropriate for these data. An outlier is an observation that lies far away from the other observations. Outliers in the y direction have large residuals. Outliers in the x direction are often influential for the least squares regression line, meaning the removal of such points would markedly change the equation. Let's take a look at the percent outsourced maintenance versus percent flight delays again. So with all the data here, we have an R value correlation coefficient of -0.6 and the equation of the regression line. But notice that the data point for the Hawaiian airline seems to be fairly far away, as does the Continental airline. So if we eliminate the data point for the Hawaiian Airlines, notice the R value, the correlation coefficient, changes quite a bit. Now it's -0.4, not nearly as strong. And the equation of the regression line changes as well. This might be considered an influential point, an outlier. There are some cautions about correlation and regression. Both of these describe linear relationships only, not curvilinear, not cyclical, or any other type. Both correlation and regression are affected by outliers, by influential points. Always plot the data before you do any interpretation. And beware of what's called extrapolation. That is, predicting outside of the range of the observed values. Beware of lurking variables. These have an important effect on the relationship among the variables in the study, but are not included in the study. Always, correlation does not imply causation. That is to say, just because two variables are strongly associated does not mean that one causes the other. So, as an illustration of extrapolation, suppose we have Sarah's height plotted against her age. The regression line and its equation are shown here. Can you predict her height at age 42 months? Well, we'll use the equation of the regression line to do that. So, we take the equation, plug in 42 for x, and we find that her height is predicted to be 88.04 centimeters. Right about there. Now, can we predict her height at age 30 years? That's 360 months. Well, sure we can. We'll use the regression line, the equation, and there she is at age 42 months. At age 30 years, we predict using the regression line that she's 209.8 centimeters. Okay, that's nice. So she's predicted to be 6 foot 10.5 inches at age 30. Notice the point at 360 months is well outside of the observed values that we have for this particular model. So it's dangerous to predict outside of that. We don't know what's going to happen beyond the observed values. Now, as far as lurking variables, Let's take an example. Does having more cars make you live longer? Well, if we did an association between them, we'd actually find that, yeah, there probably is a strong association. The explanatory variable here is the number of cars. The response variable, life expectancy. But the explanation is is because of a lurking variable. People with more cars tend to be more affluent, and affluent people tend to live longer because they have better medical care. All right, so correlation does not imply causation. Even very strong correlations may not correspond to a real causal relationship. That is, changes in X actually cause changes in Y. And the correlation may also be explained by a lurking variable. So here's an example that looked into the question, does the lack of social relationship cause people to become ill? And in this study, there was a very strong correlation. Well, is it the other way around, that unhealthy people are less likely to establish and maintain social relationships? So in other words, the relationship is reversed. Or is there some other factor that predisposes people to having both lower social activity and becoming ill? To actually begin to find causation, which is something we like to do. Does this cause that? One of the most widely used methods is called an experiment to establish causation. But those are not always possible. For example, does smoking cause lung cancer? Well, we have a lot of evidence to suggest that it does, but we've never actually done an experiment because that would be unethical. We take a bunch of people and we make them smoke a whole lot and then wait until they get lung cancer. That's not a good thing. So there are other things that we can do if an experiment is not possible. So, and then we combine all of these things together. So first of all, the association between the two things needs to be strong. For example, smoking and lung cancer are very strongly associated. The association needs to be consistent. That is, the connection between the variables happens in repeated trials, and the connection happens under different varying conditions. So among different groups, among different ages, among different countries, and so on and so forth. Higher doses are associated with stronger responses. So in other words, the more someone smokes, the more likely they are to get lung cancer. And the alleged cause precedes the effect in time. So X always happens before Y. That is, in most observed cases, smoking happened and then lung cancer happened, not the other way around. And the alleged cause is plausible, so there's a reasonable explanation. Okay, let's look at a case study here. Suppose we have the per capita gross domestic product and average life expectancies for some countries in Western Europe. Is there a relationship between these? Is it linear? And what's the strength of the relationship? So first we do a scatter plot of the data. And then using computer software like StatCado or Excel, we can obtain the equation of the regression line. Okay, that's very nice. Now, the correlation coefficient, again using software, computer software, we find to be 0.8094. That's a fairly strong positive association between the variables. Lastly, the residual plot shows only random variation of the residuals. So this indicates that a linear model is appropriate. We conclude that there is a fairly strong linear association between a country's per capita gross domestic product and life expectancy. So the higher the gross domestic product, the longer people tend to live. To review, the objectives we had were to quantify the linear relationship between an explanatory variable and a response variable. We can use a regression line to predict values of y for values of x. We calculate, interpret residuals, and we describe some of the cautions about correlation and regression.